plan for today talk is that we have a couple of questions, and as I understand, you even prepared for the answers with slides, so that we entertain the audience. I would like to start with some personal things about you, because we heard your biography that you were professor here and president there, but we didn't hear anything about the very beginnings. And I know that there are few high school young students in the audience, so I would like to start with the question whether, when did you, do you remember at all when you decided to become an engineer or studying things like that?
Okay, yeah, thank you. Thank you for your first question. And it's a little bit long story. I don't know about, say, the history of Hungary in, say, 1960s and 1970s. Anyway, I have a quite different experience compared with Hungarian people at my age. And the senior Hungarian people may know that China suffered a lot from 1966 to 1976 due to the so-called Cultural Revolution. And at that time, or during that period, the Chinese university did not provide any formal education, and even most of them were closed. So after my graduation from high school in 1974, I went to a small factory to be a repairman, to repair various kinds of machines. And then later on, in the middle of 1977, Mr. Deng Xiaoping returned to the political center of China, and he decided to change the order, or so-called reform in China. And anyway, just by the end of 77, the government decided the reopen or resume the order of education, research, and industry. So, and that year we had the national entrance examination, and Mr. Chairman just mentioned about short history in the very beginning to introduce me to the audience. Then anyway, I applied for the program of theoretical physics and applied physics rather than engineering. And I was a lucky bird to be admitted to Shandong University of Polytechnics, and nowadays it's called Shandong University. And by the program of mathematics. So I was not very pleasant. However, my mother told me that major was not so important, and you'd better to go to the schools. Okay, I adopted her suggestion and become a student majoring in mathematics. In this university, the most famous professor was Liu Xianzhi. He served as vice president and provost. He had a very strong academic background. He received his bachelor in mathematics from Peking University, and then went to Technical University of Berlin and studied mechanical engineering, and then later on moved to Göttingen to pursue his PhD under supervision, joint supervision of Professor Ludwig Prant and Professor Schuler. So he was a very well-known scientist in mechanics. He studied, say, hydraulics, thermal elasticity, mechanical vibration, and so on. Since he's provost, he then decided to resume the program of engineering mechanics in the very beginning of 1980. From his background, the students in engineering mechanics should have solid background in mathematics. So he decided that in the program of mathematics, every student is eligible to apply the transition from mathematics to mechanics. Then I record my experience in factory. At that time, I learned a lot of things about mechanical engineering, including, say, mechanical drawing and some simple formulas to design, for example, the diameter of a shaft, etc. So then I think I have enough background on mathematics, so I applied for the transition. So if you look at the initial motivation, I simply tried to utilize my previous experience in factory to let be useful rather than a waste. So that's the story.
Yeah, and also understand that your mother was a strong motivation.
Oh, that's true.
Okay, so that time was kind of the beginning of the space age in China, right? Mm-hmm. Because in the 70s, from the 70s, early 80s, mm-hmm. And I guess you did not start with space projects your career. So what was the first case when you were involved in space related work?
Okay, let me go on and. As all of you know that I received my PhD in Nanjing University of Aeronautics and Astronautics. If you look at the name of the university, you will think that, oh, the university, say, focusing on both fields. And actually, this university initially was focusing on aviation and what I mean aeronautics only, rather than space. So in the very beginning of my academic life, and I studied a lot of dynamic problems of either airplanes, helicopters, and even, say, tactical missiles, etc., rather than space. And however, later on, especially in the beginning of this new century, and China's space engineering entered into a new stage and planned a lot of missions. This attracted me a lot. So about 2004, and my team members at NUAA started to study the control of tethered satellites. This is the kind of space problem, and let me show you what it is. Okay, the left picture shows you the tethered satellites. Actually, we have a major satellite and then deploy a thin tether. At the other end of the tether, there is a sub-satellite. This way, we have two satellites connected together. It's a very useful technique. For example, you can let these two satellites flying together to form a specific shape. This way, for example, if you put one radar at your major satellite, the other radar at the sub-satellite, then you will have the connection of two radars with a very long baseline. This way you can increase the resolution of your radar detection. Okay, the right two pictures are some engineering projects before entering into this field. Then I moved to Beijing Institute of Technology in 2007 and called BIT. BIT was majoring in space engineering even in the earlier 1950s, as soon as Chen Xuesen returned to China. And when he decided to establish the whole program of China's space engineering, he investigated several universities and thought BIT was suitable to develop solid rockets. And so BIT had a very good foundation in space engineering, so I decided to establish the lab to do something different from those in NUAA. Then at that time, my most favorable topic is large space engineering structures, because I know the requirements of space industries. Then I recruit my first postdoctoral fellow, Professor Tian. He's now here, and I recruit the first PhD student. Then we initiate our study based upon the three persons, they, and now we can do a lot of things. Yeah, that's the end of my beginning of the space research. Okay.
Yeah, my next question is very easy to ask, but it's probably very difficult to answer. And it is that what is, I know you have a lot of achievements in your professional life, but what do you consider the best achievements, the biggest thing which you have ever done so far? Because it's not the end, of course.
That's really a difficult, or most difficult question. And I would like to say two of them. Regarding to the fundamental research, I prefer to talk about the earlier study of dynamics of carbon nanotubes. And maybe most of you will feel strange that the carbon nanotubes is so far from the space technology. Let me show you the picture to see what it is. And actually, in the very beginning of this century, before the China space entered into the so-called spring, at that time, we did not have a lot of money. I don't know. I didn't know what I can do. And however, at that time, the carbon nanotubes becomes very hot, and a lot of people are studying the mechanics of carbon nanotubes and graphene later. And from my point of view, I don't think the previous studies are good enough because they based upon the study, they use their model based upon the homogeneous continuum mechanics. However, as you can see the picture, the carbon nanotube has some microstructures. In physics, people know that there are several layers of atoms, carbon atoms. So according to their study of prediction, the wave problems has some troubles. And here, the bottom picture shows you the numerical simulation of my students, Dr. Li Feng Wang, based upon the molecular dynamics with the black dots. And however, you cannot get agreement with any, say, continuous mechanics results. Then what's the problem? And I told Dr. Wang that maybe you need to look at the microstructure of the carbon nanotubes, simply because I learned rational mechanics many years ago when I was a PhD student. And at that time, I was quite interested in the local or microstructure of a continuum medium. And then Ms. Wang adopted my suggestion and simply introduced one parameter, the distance between two layers of atoms. Then he got right answer and confirmed my guess. And this study has triggered numerous studies, and the citation, we have two papers. The citation have been around 1,000 or so. Anyhow, I think the result is very simple but elegant. I prefer to simple result, and maybe this is the way or the idea of Theodor von Karman. Try to get the simplicity of your studies. Regarding to the practical research, maybe the best or the most important thing is the recent study on deployable structures, and because the approach we established with Professor Tian and other colleagues in BIT get very high evaluation of industry people, and the industry people, we can solve a lot of, say, similar problems, in particular when your space structures become very soft, such as cables and mesh, etc. And for example, I can show you this video shows you the deployment of the antenna with mesh reflector, and just as I told you in the previous lecture. And here is the deployment of even more complicated space structures with 7 hexagon modules that we are interested in later, in near future. Okay, I think that's enough, and I'm not going to talk, say, the third achievements. Yeah, thank you.
Yeah, actually, I asked one, and you told two, so that's already fine. Coming a little bit back to the space projects, can you actually count how many satellites or spacecraft projects you were involved in? And can you mention a few? And in particular, I'm interested because you mentioned some projects here, but you didn't mention human spaceflight, which also has deployable structures, I guess. So just by accident, were you involved in any of the Chinese human spaceflight projects?
Okay. And as you know, China has completed the space station recently. However, most of the technologies are based upon the previous studies, maybe 15 years ago, even 20 years ago. And China began to study the space station exactly in the spring of 1992, 30 years ago. So I entered into the space technology a little bit late. When I entered into this project, I found that maybe most essential problems have been solved, and I do need to do many more. However, some of my studies are closely related to the space stations. For example, I'll give you two examples. Usually, for example, we have the highest organization called Office of China Space Station. Usually, the office will ask some individual teams or research groups to do the simulation to verify their engineering design and independently, and then they can confirm whether the design is optimal or not. And here is an example before the space station was completed, and we were invited to do the simulation of the process when the robot mounted on the space station grasped a lab cabin and then turn it to, say, 9 degrees and then fix it into the other adapter. Actually, it looks like a simple numerical simulation. You can complete it based upon commercial software such as Adams. However, actually, there are detailed problems such as the contact. The contact is one important study topic in my team at BIT. And the other is that actually there are some joints, either with lubricants or not. That's also very specific area of Professor Tian in my team. So anyway, we completed the simulation. Then from top picture to the bottom picture. And of course, this is a kind of a simple simulation, support the construction of the space station. And meanwhile, the Office of Space Station called the proposal all over the world for the space test right now and in near future. And my proposal has been adopted, approved by the office. We're going to do an orbit test to verify our techniques of satellite, tethered satellites that we began our study almost 20 years ago. So I hope this test can be completed in orbit before 2026. At that time, I would be 70 years old. And here, I show you the basic idea. And we are going to use the cargo ship to drop off the completed term of a satellite, and then it will have the spinning deployment of 2 satellites. To my knowledge, there is no any, say, test like this in the history of human being. And our partner will use the new radar to detect the fall process of the spinning deployment. And we also have the terahertz telecommunication to complete the control. After the first stage of the deployment, the main satellite will then drop off a sub-satellite to about 200 meters long and also verify our techniques. And this is the proved project or proposal by the China Space Station office. I hope it can go in well later. Yeah, thank you.
So, thank you. You started with saying that there are no problems, but then of course the obvious way is to make a problem and then you can solve it. So this is the experiment. Okay, in the last 20 or even 10 years, more like 10 years, we hear a lot about Chinese space program, like much more than before, and it's like flourishing. What is the main motivation behind this? What do you think in China? Well, the great support which the space program receives.
Yeah, this is the even greater topic, and let me try. Well, from my observation, of course, and the motivation or drive of space programs in China includes several parts, I believe. For example, the first part comes from scientists who are eager to know something new, and for example, whether there is water in other planets except for the Earth in solar system, and if there is life in, say, galaxy, for example, and of course, this is the first part. And the second part, maybe I think plays more important role coming from the engineers. We are eager to create something new, try to create for example, the world record. And for example, we are interested in to establish the laboratory on the moon, and we are interested in sending Chinese astronauts to the Mars, for example. Of course, and even though the number of engineering people are much more than the scientists, however, I believe the third part is most important. That comes from the government. They pay. Nowadays, the government believes that the space technology is very useful and offers the society of, for example, the weather forecasting and vehicle navigation, wireless telecommunication, etc. For example, and the World Meteorological Organization has 8 centers in the world to offer the weathercast information. The Beijing Center is the most important one in the Far East countries to offer the accurate information, weather information for East China and West Pacific Ocean, and based upon the satellite. And to my knowledge, the weather forecasting satellites of China are on the very top position. And so this is very useful. And by the way, the government believes that the space technology can promote a lot of new areas of engineering, such as advanced materials, especially lightweight structures, etc., and then computers, artificial intelligence, etc. So their beliefs is correct, and the past 20 decades prove that. And space engineering really, say, promote and leading a lot of areas in China to advances very fast.
Speaking about the near future, what do you think will be the greatest record, what you said, the world record, like putting a man on the moon or what, in 10 years, so to say?
I did prepare something for this question because I'm not able to say the story by words only. So I prepared 3 slides to show you what we are going to see in short future. I don't know any people here have read the white pages of China's space programs announced last year. And over the past 2 decades, Chinese government will issue or announce the white pages of space programs every 5 years. And in recent white pages, you can get a lot of information. I copied an English version of the white pages in this computer, and any people, if you are interested in the white pages, then you can make a copy. Now let me tell my observation or prediction, just from, say, my experience or my interest of dynamics. Okay. Well, the first important mission in deep space exploration will be the detection named by TW2. I told you that TW means Tianwen, a well-known name of a poetry, to explore the universal rules. The Mars exploration was TW1, and TW2 is going to detect an asteroid numbered 2016 H03. It means it was discovered in this year. This is a very special astronaut because from the picture you can see, and here is, this is the moon, and this is the Earth, and the white curves are the Earth orbit, and the red circle means the moon's orbit. And this asteroid flying around the Earth in the yellow region, quite chaotic. It's not a periodic orbit, so it looks like something on Poincaré sections in nonlinear dynamics. Anyhow, most people think that this asteroid may be a little bit dangerous because the distance between the asteroid and the Earth is not very large. It's about 14 to 38 million kilometers. And you know the distance between the moon and the Earth. So it's just between, say, no more than 10 times of the distance. So people are very interested in this asteroid. However, we don't know the exact shape and exact size. What we can do is only to use radar to detect, say, approximate length of the long axis and the short axis, and if you assume that it's ellipsoid. However, most of the astronauts are not have the shape of asteroid. Here is an example detected in 2012 based upon the research of BIT faculty members. After the mission of CE2, and this mission still have a lot of fields did not use up, and then people discussed what is the extended mission for this detector. So later on, the BIT faculty members designed a proper trajectory for the CE2 and then fly to 6 million kilometers from the Earth and take a very clear picture. Before this picture, and the American radar told us that this small asteroid looks like an ellipsoid. However, the picture shows you that it's not the ellipsoid. As you know, the gravity depends on the shape, distribution of the mass. So you can imagine that if we don't know the shape of this asteroid 2016 H03, it's very hard for us to let our probe land on the surface because the gravity is irregular and is very weak. And your spacecraft may, just touch upon the asteroid and then cannot be attracted, then leave it. So this is a very difficult problem for this mission. In addition, China is going to sample a little soils and rocks from this asteroid and then return to the Earth. You can imagine the difficulty. And even though we have had the experience, successful experience to sample something from the moon. However, it's more difficult for this mission. This is the first example I'm going to introduce you. And you can also find it from the white pages of China space programs. The second mission I'm going to talk about is a China space mission, TW4 or 5. We are going to sampling something on the moon, but around 2030, still have 6 or 7 years. Now we are doing some preparation and study. And this mission is more difficult than the sampling mission from the moon. There are some important issues. For example, we are going to launch 2 orbiters. The first orbiter will bring, say, the landing system and the rover and the robot to pick the sample. And the second spaceship will be launched a little bit late, as shown in the figure, that after the first spaceship completed the sampling task, then launch again from the Mars office. Then we will transit the sampling soils to the second spacecraft, and the second spacecraft will fly back to the Earth. So this is a very complicated consequence of the whole work. By the way, the landing platform will be much heavier than those for the moon detections. So it's relatively very hard for us to solve the problem of EDL, entry, descent, and the landing, according to the dynamics. For example, I'm deeply involved into some discussions of those issues. I'm not sure whether the parachute dynamics is okay, because we need maybe even larger parachute. And by the way, the NUAA had a unique lab studying parachute. So this way, I pay much attention to these problems. Okay, the final mission I'm going to talk about is the CE6 or CE10. CE6 is going to sample some soils and rocks in the solar region, particularly in south pole of the moon, because a lot of people guess that there is ice over there. However, we don't know, because nowadays there is no any detections there. CE10 is going to send to at least 1 astronaut landing on the moon, also around 2030. This has not been announced, but have been well prepared. And particular, China tried to develop even larger carrier rocket, doubled capacity compared with CZ5. And I believe should be larger than Heavy Falcon 9 developed by SpaceX in the United States. And the best result of the mission will let, say, 2 astronauts drive a rover more than 1,000 kilograms, say, till and towards the final destination in the South Pole. And maybe that's too difficult, but that's some conceptual design I can introduce to you. Thank you.
Thank you. These are really exciting times, also in China. You come from the academy and university era, but it seems that nowadays in Chinese space sector, there is much attention from private companies. Mm-hmm. So they develop rockets, they manufacture satellites, they deploy large constellations of satellites. So what is your view on the private involvement in space in China?
Well, and my observation is optimistic to some extent, but not so much from the other side. And nowadays, there are more than 30 private companies related to space missions. However, most of them are in very small scales and focus on a specific purpose. For example, the solid rocket or cube satellite, etc. However, they do have advantages to make quick response to the variation of market, and they usually can be even brave, for example, to let some new techniques below the level 7. Usually in space engineering, we prefer to use the conventional technologies or the new technologies beyond the level 8 or even high. However, if you below 6 cannot be go to the sky. However, the private company relatively have more flexible from this point. However, they do have some their shortcomings, for example, and they do not have very strong fundamental research. So usually they would like to cooperate with the universities. And for example, in BIT, some of my colleagues are involved with a joint research with the private sectors. The most tough thing is that whenever you're going to send something to sky, you need to get the approval called China's National Measurement and Command Networks, and because they need to monitor the whole process of your launch. And nowadays there are so many missions in China, so usually the private company they need to wait for in the long queue, and so this time the white page of China space program mentioned about to establish the other network for the private or market purpose, or establish some independent launch site in the right base we have now. However, I'm not sure whether they can complete it. And anyway, that's a trend, and the government also tried to promote the private companies to do better. However, anyhow, their technologies and say financial abilities are still much lower than X-Space in the United States.
Yeah, well, it may change. Yeah. Coming back a little bit to your professional experience from the space. So I know that, and we heard that you spent quite a lot of time working in foreign countries. So what is your, how can you, and of course you spent a lot of time at home in China. So what is the major difference in the research environment or culture, what you experienced in your career?
Well, I received the question before my trip, and I did recall my experience. I spent about 3 years in Germany and in the United States in the middle of 1990s, about 30 years ago. I almost forget the exact feeling at that time. And as introduced by chairman, that I received all degrees in China. However, my previous tutors received their degrees either in, say, Germany or UK or former Soviet Union. So I could not recognize big difference, say, from the viewpoint of academics in research. Of course, in the old days, especially during my bachelor program, all the textbooks I use are translated from Russian textbooks. Yeah, maybe at that time I was greatly influenced by the former Soviet Union. And then when I began my master's degree and PhD degree, most of the materials I read came from the United States or UK, etc. So from this point of view, I don't think there is a big difference, say, between my education and my experience later on in Europe and America. However, if I look at, say, the specific issues, I do find some, say, difference in culture. For example, when I was in University of Stuttgart, I usually dressed very formally, like this. Sometimes maybe not suit, but I need to wear the ties. Why? Because at that time, I received the Alexander von Humboldt Research Fellow. My identity did not work for the students' cafeteria. I could not buy the dinner coupon. It's cheap for students. I could not do. And this way, I should behave or looked like a faculty member. So I tried to dress like my professor, Werner Schiller. He dressed up very formally every day. So yeah, that's a style. And then when I went to Duke University in the United States, there was no specific cafeteria for different people. And what I mean that faculty members and students share the same cafeteria. So I did not need to dress so formally. So I behave like students and wear or dress in a casual way. And actually, this is the big difference between, say, anyway, Germany and the United States. Usually, the German professor behave like gentlemen and lecture and work very carefully, seriously, and American people may be more vivid, and yeah, this is a cultural difference. If talking about the influence of these international experience, I think maybe the later visits of mine to the United States maybe played an even important role, and I received 2 times of training called senior executive training. The first one was in University of Stanford University around, say, 2004 or 03, yeah, 1 month, and the second one is in Harvard Kennedy School of Governance, and also 1 month. I read a lot of books about, say, politics, international relations, in particular, decision-making. So I got to know the big difference between a university and a company, even though we had sense. However, anyway, for me, I did not have theory. So from these executive training programs, I got some theory from the books and from professors. For example, I know the difference between the transactional leadership and transformational leadership. I believe maybe most of you do not familiar with these words. The transactional leadership means that I give you some bonus and benefits time to time to stimulate you work harder. And the transactional leadership should be influence your colleagues and share the same, say, purpose or goal of your destination, and means that there is no any transactions between your relations. And the theory emphasizes that the university should use more transformational leadership rather than the transactional leadership. However, nowadays, even in China, in Chinese universities, actually, we had a lot of transactional relations. So I tried a lot to reduce the shortcomings of transactional leadership during my term as a university president. Okay, yeah, I think that's all for enough for the question.
Thank you, very interesting. We are running out of time, so I would like to wrap up with my last question about your Hungarian connection. So I'm pretty sure you have some collaboration with Hungarian colleagues, because otherwise you would not be here. So can you just very briefly tell us when did it start and what I guess it's not space related, isn't it?
Okay, thanks for your last question. And of course, I'm very honored to be an honorary member of Hungary Academy of Sciences, based upon not only my achievements, but also the collaboration with Professor Gabor Stepan and other Hungarian colleagues. As I remember, I met Professor Stepan in the middle of 1990s. And since our first meeting, we have shared a lot of common interests and perspectives, in particular, the education and the research in the frame of engineering science. And we talked a lot about, say, Professor Theodor von Kammen and Professor Xuesen Qian, and even during his visit to NUAA, we talked about the history of the university and the influence of the school. So that's very important. Meanwhile, Professor Gabor Stepan is a leading scientist in the field of called delay dynamics. And I read his first book written or published by the end of 1980s when I was in the United States. At that time, I had a problem from my control experiment. At that time, in the very beginning, I didn't realize that that's a problem due to the time delay in the feedback. And later on, I believe that's a delayed problem. However, I did not have theory. I can consult some papers. However, I cannot focus on the theory. So when I first read the book of Professor Gabor Stepan, I was quite happy. So from the Western world, maybe this should be the Bible of the research. So later on, when I met him personally, so we had a lot of communications. Later on, let me see, in the beginning of this new century, maybe 2002, Professor Stepan participated in the International Conference of Vibration Engineering that I chaired in Nanjing, my home university. So this way he got to know my research, my team, and he enjoyed communicate exchange with my students and colleagues. And later on, he paid many visits to NUAA and delivered not only lectures, but also the formal lectures for the graduate students. They're very interesting courses. So when I completed my term as the university president, I attended the course in 2018 and enjoyed a lot. So since I served as a university president for so many years, and I was quite busy, so I can say Professor Stepan played an essential and major role in our collaborations. And my team members and students have had more than 10 papers jointly published with Hungarian colleagues. And based upon our achievements, we jointly organized 2 IOTM symposium. In the first one, Stepan was one of 6 members of scientific committee. And for the second one, Professor Inchberg, his colleagues in Hungary, in Budapest University of Technology and Economics, served as the co-chair with my colleague, Dr. Zaihua Wang. So those collaborations really are beneficial for both sides. So, and now I'm very happy to see that the younger generation on both sides had a lot of communications. For example, Dr. Zhang Li, she has been here. She has visited here many times. Once upon, she spent 1 year joint study here, supported by the China Scholarship Council. And this way, to promote the future collaboration, I invited 2 of my colleagues from Beijing Institute of Technology, Professor Tian and Professor Luo. They both will deliver lectures at the university, and we will discuss the possible collaborations in future. Okay, thank you.
Thank you very much for your willingness to answer my questions. I hope it was interesting, and I think we should finish now because it's like 12:15. So thank you again.
You're welcome.